So this is common manufactured features. So in this lecture, we're going to talk about some common features on machined and manufactured components. The first thing we're going to do is look at 3 common features called countersink, counterbore, and spot face. So countersink and counterbore, they're typically features that are designed to aid with using certain types of fasteners, countersunk cap screws and socket-headed cap screws. So I have an example of a component here that has socket-headed cap screws used in the assembly. So this is a socket-headed cap screw. All right, it has a head on the cap screw that looks like a socket. Okay, socket shape, and that socket actually has a hex head, so that we can use a hex key or Allen key to engage the fastener and tighten or loosen the fastener. So with the counterbore, this counterbore is suited to allow this socket-headed cap screw to be tightened up in the assembly, and you can see here that the socket-headed cap screw is just subsurface of this side of this bracket, and now that basically allows for this head to be below the surface so that it doesn't interfere with other components in the assembly, and it provides a nice aesthetic to this component. So we also use counterbores for other fitting of machine components, so they're not just designed for fasteners like these socket-headed cap screws. I could in fact create a counterbore for a hex head cap screw if I wanted the hex head to be below the surface of whatever I was fastening, but I would have to also think about how am I going to tighten up this cap screw. And typically we might use a socket, because a box end wrench wouldn't be able to fit into a counterbore. So I would have to make this counterbore so that it would allow for the wall thickness of a socket, so I can actually tighten the fastener up within the counterbore. So here's just a little inventor assembly that I drew up really quickly. So here is a socket-headed cap screw, and when I mate this to the assembly, you can see here that it is just flush or below of the surface, so it's not going to interfere with anything else in this machine. Another type of fastener we use, or you will see, is a countersunk cap screw. So the countersunk cap screw has a head that features a conical taper. Now this conical taper will fit into what we call a countersink. Okay, or we can say this is a countersunk hole. So again, I can allow this feature to be placed in the hole. I'll just assemble it for you. Flip that around, and there we have our countersunk cap screw is nice and flush with the top surface. Now, other mentions for this countersink feature. So again, it's not just for countersunk cap screws. If you've ever taken the wheel off your car, the wheels on our car use lug nuts, and your car rim, where the bolt hole pattern is, has countersunk holes around the rim, and what that does is these countersink features sometimes allow us, like in the case of the car rim, it pilots, it centers the wheel, centers the fastener so that the wheel is lined up and concentric with the axle or the front spindle of the vehicle. So these are really important features, and not to be taken too lightly. The other feature is called, and I'll just circle this here, this is called a spot face. And what the spot face is, it is the same geometry as a counter bore, okay, but it is shallower. It's not typically as deep as a counter bore. And you might say, well, it's the same thing as a counter bore, because it is. The geometry is the same. But what a spot face is it is a feature that, again, the geometry is the same as a counter bore. It's just a cylindrical feature. But what it is it is a feature that's not controlled by specifying a depth. So if you look at the counter bore feature here, and this nomenclature here, this decimal 25, this refers to the size of the hole. It's 0.25 or a quarter inch. It's going to suit a quarter-inch fastener. The counter bore, this decimal 5, is referring to this diameter here of the actual counter bore itself. It's a 0.5-inch counter bore, and it happens to be 0.18 in depth. So with a counter bore, we specify the depth. With a spot face, we don't specify the depth. It is up to the machinist or whoever to give it a quick spot face. And you might say, well, why would I want that? Well, the less dimensions or specifications on a drawing, the more economical it is. Because now the spot face depth, what we're doing, we don't have to pay somebody to measure on an inspection report, quality control, how deep this feature is. Because its purpose isn't necessarily to shroud the head of a bolt. Okay, and I'll show you an example on a future slide here. Let me scroll ahead, and I'll show you where. So this could be a bearing housing or a casting, and the one on the left is the casting before it's been spot faced. So the problem here, do you see this gap between the bolt head and this angled surface? If I go to tighten this bolt down, the bolt's going to make contact on this side, okay? And as I tighten this down and the thread stretches and elastically deforms, it's going to get to a point where I'm going to create a stress riser here, and I'm going to pop the head. The head of this bolt is going to break off because it's not making even contact on its lower surface here, and therefore it's going to shear. It's going to break away and fail. So what can be done here is we can add a spot face. We can come in with a machine tool and give this thing a little machining with the machine tool, and in this particular situation, maybe the depth is not so critical because we have a nut and bolt assembly on the other side, and we can tolerate some difference in some variation in this depth of this spot face. So now that that is not specified, this is a little more economical to produce. I don't have to have somebody check the drawing and say, well, there's a counterbore there. Did the machinist machine at the right depth? No, because that's not in this context, in this scenario. It doesn't have to be that critical. The depth, there's a lot of tolerance in the assembly to allow for a wide variation of this spot facing. So someone's going to see the spot face designation on the drawing, and they're going to plunge into the material enough to produce a nice flat landing for the bottom of this bolt head. Okay, so that's where we would use a spot face. We also use spot faces for, and I'll try to do this in a future video, for just assembling components. We might have a cylindrical type component mating with a flat surface like so, and the spot face allows for a nice clean aesthetic, and I'll have to show you that in a video, in a future video with some examples that I have at the college that I'll bring in or bring home so I can record for you. Before we move on to the other features, I want to just talk about, this is in your textbook, figure 8-8 in Unit 8. We can use words to describe these features, So as the figure title here says, we're using words. So we're using abbreviations: CBOR for counterbore, deep, CSK for countersink, S face for spot face. This is a little more traditional, a little more old school. What you'll see more common is the symbolic method. So let's look at the spot face. This first value here, this decimal 2.8. Well, it has to be this size right here. It can't be the 0.5 because it would be larger than the spot face. So this is what the 0.28 is referencing right here, this diameter, and the 0.5 is this one here, 0.50. A little messy for you. So that is the diameter of the actual spot face itself. So the symbols are all right here on the left. Okay, the countersink. The countersink, again, the decimal 2.8 is referring to we call this the hole size. Because really, you could say, well, this is a hole, but the hole size is the size of the cylindrical feature that is going to suit or be sized for the fasteners that we're using. So this is a decimal 2.8 hole size, and now this little V-looking symbol here, this just is telling us that there's a countersink. Okay, because if you didn't have this side view, how would you know if this was a countersink or a counterbore or a spot face? You wouldn't know. So this symbol, little V symbol, means countersink, and then the decimal 5, again, it's speaking to the overall diameter of that. This is the 0.5 right here that they're talking about, that diameter. And then the 82 degrees, what that is it is the angle of separation between the two conical edges. So the 82 degrees is this right here. This is 82 degrees. Okay? That is what that angle is referring to. Okay? The counter bore has and this slide's not showing a depth, but it's showing here that there's a 0.28 hole again with a decimal 44 counter bore. That's the overall diameter of the counter bore. But they're missing the depth on this particular slide. So there should be a depth symbol to be more accurate here, like so, following this, so that you could have a depth of that counter bore. And now the hole, the plain hole here, oops, I lost my slide. The plain hole that has a 0.28 diameter, and it's now drilled to decimal 6.3. So the depth symbol just is placed after the diameter, so this is referring to the hole. If I had a depth symbol after the counterbore, it would refer to the depth of the counterbore. It's just, you just read this thing in order and think through logically. Now I'll ask you this. This 0.63 depth here, this right here, what do you think that is referring to? Is that this depth, or is it this depth? Which one is the 0.3 referring to? Think about that for a second. While you're thinking, let me switch over to my trusty camera. So here's just a typical drill, and this drill has a drill point, and it has basically a conical shape to it. So when this is drilling into material, once I plunge it in the specified depth, it's going to leave a conical impression at the bottom of the hole. Okay, so these are typical angles that you can find specs on in the machinery's handbook. And if I go back to the slides, what I will tell you here, so you know the answer, is this depth is referring to the functional part of the hole. Now this tapered or this conical depression here is not a functional part of the hole. Meaning, if I were to insert thread that hole and insert a screw, this thread of this cap screw is not going to engage with that tapered or that conical portion of the hole. It's not functional. So that's not the functional part of the hole. So the 0.63 is referring to the functional part of the hole, so it's not including the conical depression. So this is important to know. This dimension here is the 0.63 depth. Okay, that's what that is referring to. And there's actually a typo on this textbook image. So in your book, you can cross this out. This is not a diameter of 0.63. This should just be 0.63. So this is 0.63 inches in depth. Okay, not including the conical depression because it's not functional. So here, this is a little textbook activity. You should try this out. We looked at this when we were talking about sections. This has a full section view shown in its front view. You should go through this activity. This component has some examples of counter bores. So there are a couple of counter bores here, here, and even here. So this may not be designed for a fastener. There might be a shaft component or something fitting in here. These two are definitely for to suit socket-headed cap screws. So you should do this activity. So here's that slide I previously showed you on the spot facing. And let's talk about undercuts and chamfers. So undercuts, chamfers are designed to aid us in putting parts together. Now what you will see here on the left is this component has a filleted or a radius between where the shaft steps up to a different size, and you could see here this would interfere with the fitment of these components. So what has been done here is they've undercutted the component using a parting tool on a lathe, so that now we can fit this component and the surfaces sit flat against each other. So undercutting is a quick and dirty way to do this, to achieve this. But undercutting does have a major drawback because it's now reducing the diameter of this shaft, and we have a new weak link. So it's not as strong as it is at the full diameter. So the alternative is to chamfer. So put an edge or an angle on the leading edge of the hole so that it will clear. I use that word clearance in a different way. It'll clear this radius or this filleted feature. The filleted feature is going to provide more strength over something that was machined to a 90-degree corner. We talked about that in a previous lecture. So we want this radius shape. If you look at shafts on your car, journals on crankshafts, trailer axle spindles, they all have a radius when we step up or step down the size of the shaft where there's a bearing fit. And the bearings, the inner race of the bearing, will have a taper or a round on it so it can clear this fillet on the shaft. We don't want stress risers in our designs. So these are important features. And you might argue and say, well, a chamfered hole appears to be like a countersink, and yes, that's true. It is similar geometry to a countersink because it's a conical shape in all essence, but its purpose isn't to align a fastener or anything. Its purpose is to break the edge and provide some clearance for a mating component. So chamfering also allows us, if you look at the end of this shaft here, the end of the shaft is also chamfered here, this angle here. Now that chamfering allows, I said this before in this lecture, piloting or aligning. This component might have to be pressed in. There might be an interference fit, meaning the shaft is larger than the hole, and we might have to use a press or a heater to expand the size of the hole, and then when it cools it'll shrink. It's called a shrink fit. So when we use a press to force these two components together, having this angled or chamfered edge on the shaft allows for piloting and alignment, and so that we can force these components together. So that's another application of the chamfer. Okay. So here's how we dimension undercuts and chamfers. So what's shown here is in the first little figure here, this 0.6 by a diameter of 1/2. What it's saying is, look, this overall diameter here is 0.64. The diameter of the undercut is 0.5 inches, and it's 0.6 inches in width. So we use a parting tool that's 0.6 inches when we turn this down, or we neck this down. The other one, so this undercut has a radius, a little bit of a better design. There's more cross-sectional area here. Still not as good as just the regular old fillet. Still not as strong as that, but it is what it is. This radius is now 0.06, and the diameter is a half inch. Okay. And now dimensioning for chamfers. So if it's 45 degrees, we can chamfer it this way. We can just show the angle right here, and then the diameter of the largest diameter, and therefore we could do the math if we really want to know what this inner diameter was, but most likely this hole would be specified somewhere on the drawing as something. For angles other than 45, so for instance it's 30 degrees, we're referencing from the OD, and we are referencing that angle from that horizontal surface or edge. Okay, and then in this case we have to specify the length of that chamfer, because again, because it's not 45 degrees, this length is going to be different than this will be different than this, because it's not 45 degrees. So knurling is just a process where we turn a component on a lathe, and we force two wheels that deform the surface and create a pattern. So here's an example. I'll just show you a tool that I have, and here's a ratchet, and we do this. This thing will turn on the lathe, and there's two wheels that have the opposing angled pattern, and what happens is it just is forced into the surface, and it's like if you took your hand and pushed it into some Play-Doh on the table, you would have peaks and valleys. So wherever my fingers touch the Play-Doh, I'd have peaks and valleys that would fit between my fingers, because the dough has to go somewhere. Well, the metal has to go somewhere. When we knurl something, because of the nature of the process, we're actually increasing the diameter some amount, because theoretically we're displacing material. So this just allows us to provide some grip. Here's a valve stem removal tool. Again, this thing is knurled, so it has some grip when we're using the tool. So that's knurling. So we can do straight knurling or a diamond pattern. Um, here's some other common features. So typically, like on say a big AC motor in a factory or a gearbox, we call the large flange where we're going to bolt it down. We call that part the lug. So this is the lug, and then whenever we have a raised portion, this is called the boss. Obviously, you know that's a round. We've got fillets, countersinks, counterbores, chamfers. So just here are some of these things in practice. So that's it for this portion of the lecture.